Felix. And thanks again to the organizers for putting together such a wonderful conference and for giving me the opportunity to speak here today. I wanted to also mention something about Misha Klein. So for many years I've been placing either the credit or the blame, depending on how you look at it, on introducing me to association schemes to Bill Martin, because he really converted me to working on these problems. But actually, when I was at University of Delaware, Misha Klein was visiting for a year, and I sat in on an algebraic combinatorics course, a topics course that he was teaching. And this course did put an impression on me, and when I graduated, my brother offered to buy me a book as a graduation present. And so the book I asked for was Distance Regular Graphs by Brouwer, Cohen, and Neumeier. And so he tracked down a copy of the, at that time, out-of-print book for me. And so when I arrived at Bill Martin's doorstep, I had this book already in hand, making my conversion that much easier. So thank you, Misha. What I wanted to talk to you all about today is Q-Polynomial association schemes, which is the problem that really got me hooked into the area. And since then, I branched out more to coherent configurations. But recently, I've returned to this problem and tried to look at it with fresh eyes and see, well, there's still a lot of work to be done. So just in case you've dodged all of the sessions that have defined association schemes. So first of all, I'll only be talking about symmetric association schemes, and fairly soon I will stop saying symmetric, but it will be implicit. So you have a set X and a set of relations, partitioning X cross X. The identity is one of them. They are all symmetric, and then the key property is the existence of these structure constants, Pij, basically saying that any k-related pair looks like any other k-related pair if all you're doing is these basic counts. Now, if you look farther, there may be differences, but so I think of this as a local symmetry condition. Just things look the same if you don't look too far. And when I first saw this definition was really in a finite geometry class, and I had no idea what to make of it. But Bill and Misha were very good at persuading me as to the fact that these come up a lot and that there are very many useful tools here. Okay, so I'll briefly mention the prettiest examples. So if you have a group which is so-called generously transitive, it's a transitive group on a set, but for every pair there's some element in the group that swaps the two. Then you look at the orbits of this group on x cross x in the natural action on x cross x, and you get a symmetric association scheme. And so these are the prettiest ones, and we'll call these Schurian, and here is just the dihedral group acting on the hexagon and the orbitals that you get from it. All right, so I may mention whether or not a scheme is Schurian or not. One of the things that surprised me initially when I looked at this is not only how many schemes are not Schurian, but not even vertex transitive. So, if you're not as familiar with these objects, if you just sort of think of this example or these kinds of examples, then you have a gist, but actually there are plenty of examples where the automorphism group is actually trivial. So these local symmetry conditions do not imply any kind of global symmetry, at least not in general. Okay, quick word on imprimitivity. So if you look at the graphs so you can, since all these are symmetric relations, we can just think of them as graphs if we want. And if any of the graphs, except for, of course, for the loops, are disconnected, then we call the scheme imprimitive. And imprimitive schemes are naturally, well, in some sense built from smaller schemes. There is a natural subscheme and a quotient scheme, and there's you can partition the points into sets, and certain relations appear in the sets and certain between. I should point out, though, that if a scheme is imprimitive, the quotient and the subschemes can be very trivial, and yet the object itself may be very interesting. So imprimitive doesn't mean boring. So like incidence graphs of projective planes, the subschemes are complete graphs, and the quotient is an edge, and yet those are very non-trivial objects. But still, if you're looking for association schemes and they're imprimitive, you can look at what the associated primitive objects are, and that may tell you something. Okay, so the driving force behind that last local symmetry condition is that from it you get a matrix algebra. So just define adjacency matrices for all of these different relations. And the PIJKs are basically just structure constants of this matrix algebra. And it's an algebra of symmetric matrices, so it's going to be commutative. Also, that was part of the definition of the PIJK, really. So we can do this, take the span of these matrices and get a matrix algebra. You often do this over complex numbers, but I'll only need real, because again, everything's symmetric and diagonalizable over the real numbers. So we're going to call the algebra generated by these AIs the Bose-Mesner algebra of the association scheme. Now, since it's a commutative algebra of real symmetric matrices, we can just simultaneously diagonalize the whole thing. So for what follows, if you just think of diagonal matrices, then actually it's fairly obvious what's going on, that you get a decomposition of r to the x into d plus 1 common eigenspaces of all of the matrices. And one of these is obviously going to be just generated by the all ones vector. So we have that eigenspace, we'll set that at v0, and then we have a collection of other eigenspaces. Okay, well, we have eigenspaces. We can talk about the idempotents that orthogonally project onto these eigenspaces, and it's not hard to see these are in the algebra too. If you want to write down a quick proof, think of them again as diagonal matrices, and it's completely obvious. And, well, these are orthogonal eigenspaces, so matrix multiplication with these is trivial, and these idempotents form a second basis for which matrix multiplication is trivial. So now we have two bases of the Bose-Mesner algebra. And this part really surprised me the first time I saw it, even though it's really obvious, is that actually if you just take entry-wise products of these AIs, otherwise known as Schur multiplication, well, obviously you're going to get either AI or 0 back again. So the basis is closed under this nice multiplication, so the whole algebra is. So we have a second multiplication on the Bose-Mesner algebra. And it's completely trivial for the AIs, so we can ask what happens when you do it with the EIs. And what we get is it has to be closed, so we get a second collection of structure constants. And these are called Krein parameters. Now, these don't have to be integral or rational, and there's no known combinatorial meaning for them, but it is a very easy proof that they have to be non-negative. So I will require reference to Krein parameters at some point later in the talk, but I think it's worth mentioning that they can be computed completely from the PIJKs. You know all the PIJKs. You really can compute everything that you need here. Okay. So there is a formal duality between the matrix multiplication and Schur multiplication and these AIs and these EIs. Now, there is an actual duality that's possible, but for most of the things I look at, it's more the exception than the rule, so I'm not going to really dwell on it, but you just need an abelian group acting regularly, abelian group of automorphisms acting regularly on the scheme, and then you can actually dualize. And in that case, these Krein parameters, oops, I pressed the panic button, I think. There we go. In that case, these Krein parameters actually will be integers. And actually, you can spot immediately if the Krein parameters aren't integers that there is no dual without even poking your head into the group, if there is any group at all to really look at. Okay, but this also suggests that, whenever you look at a theorem, maybe in terms of the AIs, you can write down at least a formal dual to the theorem, and then that becomes maybe a conjecture, and you can start to wonder, is this true? Does it have any meaning? It's not obvious that it does. And that is also something that will motivate a little bit of what follows. Okay, so briefly also mention a cheap way to build association schemes using Kronecker products, in particular this bipartite double here, where I'm just taking Kronecker products with an edge. So this gives you another association scheme. Not necessarily an interesting one, but in one case it will be of use to us. So very easy way to construct a new scheme from an old scheme, which is naturally going to be imprimitive. Okay. All right, so that's all the background material. Now we get to polynomial association schemes. So association schemes, there are many, many different kinds. And in 1973, Delsart in his thesis, he wrote his thesis looking at algebraic methods in coding theory and design theory, and he identified these two particular kinds of association schemes because he noted that techniques that he could apply to the so-called Hamming schemes, these are schemes just given by the n cube and distance in the n cube, and Johnson schemes, which you just take k-element subsets of some fixed set. And he could apply them actually to a larger class of schemes. So p-polynomial schemes, basically you have one matrix A1 that's generating the entire association scheme in a nice way. Now actually for A1 to just generate everything in terms of polynomials, you need it to have d plus 1 distinct eigenvalues, and that'll come up later. But p-polynomial has a slightly stronger criterion that you actually want ak to be a degree k polynomial of A1. So you want the degrees to grow as nicely as possible. And this turns out to be equivalent really to just saying that A1 is the adjacency matrix of a distance regular graph of diameter d, and that the whole scheme is just distance graphs of this one graph. All right, and this is, I would say, the most well-studied kinds of association schemes. But he also defined a different notion, that of a Q-polynomial association scheme, which is basically the formally dual notion of that of a p-polynomial scheme. So you take the idempotent E1. In this case, E1 has to have d plus 1 distinct entries, because now what we're going to do is take polynomials of E1, but using the Schur product when we do the polynomials. So we need it to have d plus 1 distinct entries to generate the whole association scheme. And now we require that ek is a degree k polynomial of E1. And so again, the degrees are growing as nicely as possible. So you wonder, is there any relationship between these two properties? Certainly, there is a lot of work that's gone into studying the schemes that have both properties at the same time. There's also a conjecture that for sufficiently large d, so if the number of classes is big enough, if the scheme is primitive, then these two properties should both occur or both not occur. And it's hard to say. I for a while was convinced of this, but later I'll mention why I'm not so sure if this is true or not. The primitive is actually needed here. There are, albeit not many, examples where there is an imprimitive scheme that's d is going to infinity, but it's, say, q but not p, or p but not q. Okay, so where was Delsart coming from? So he was looking at coding theory and design theory, and in his thesis he came up with a general bound, the linear programming bound, which I'm actually not exactly going to talk about here, but he also started examining when this bound was tight and came up with notions of so-called capital T designs. So basically what you look at is take some subset of your association scheme, and we'll say the association scheme is Q-polynomial, and we've ordered the idempotence appropriately. And we take some subset of indices, and we just say, okay, well, suppose I take the characteristic vector of that set, and it vanishes on all of the different idempotents in this set capital T, indexed by this set capital T. And we call that a capital T design. And then in the case, very special case, where the indices are all consecutive starting at 1, we call that a lowercase t design. Okay, so, and he noted that in the Johnson scheme, which the Johnson scheme is a Q-polynomial scheme, that, so now we have really a set of k-element subsets that we're looking at. And what does it mean for it to be a t design? In that case, it's exactly that it's a t vk lambda design. And then he looked at many variants of this for other capital T's and could derive other interesting combinatorial structures from that. And from that, he made an in quotes conjecture in his thesis that and basically explaining his motivation for the general definition up top, that in general, capital T designs will often have an interesting structure. I'm assuming in quotes because you really should phrase it a little more carefully, you know, that T probably should be big relative to some other constraints. But that in general, you know, this is a way to locate interesting things or describe interesting combinatorial objects inside other ones. So he also was able to come up with certain generalizations of theorems. So there are these theorems that if a T design doesn't have too many block intersection sizes, then actually you take the block intersection sizes as relations and actually you get an association scheme. So I think in maybe a couple of talks here, people have mentioned quasi-symmetric designs. So you have a 2 design with 2 block intersection sizes, and they mention a strongly regular graph being associated with such a design. So of course, a 2 design could have many more block intersection sizes than that. So that's an example of such a design. Well, he came up with a general bound. So take a subset, and in this case, if you want to think of it as the Johnson scheme, but it can be any Q-polynomial scheme. And we're going to say all these idempotents, when you multiply it by the characteristic vector, they all vanish for 1 to t. And what I'm going to let is S be the number of relations that appear in the subset. And as long as S is not too big with respect to t, then you can just restrict all the relations to y, and you get a Q-polynomial subscheme. So yeah, again, designs with few numbers of block intersection sizes are a special case of this. And quasi-symmetric designs, some of the WIT designs, like the WIT design on 11 points has 3 block intersection sizes, and the 4 design. But also, just in general, you get Q-polynomial subschemes of other schemes. So there's a larger theorem here for more different kinds of association schemes. And there are other generalizations of this. One here is by Brouwer, Godsell, Colin, and Martin, and it has to do with the so-called dual width of a scheme. So it's almost the opposite. Instead of wanting, say, the first t idempotents to vanish, instead what you want is the last collection of idempotents to vanish and have that interval be big. So I defined here the dual width, which is just, you know, what's the largest I for which this doesn't vanish. Of course, it's possible that's just d, which is not very interesting in that case, but it could be something smaller. And they came up with a bound for the dual width, and if it's tight, again, S is the number of relations in the set. And if this is tight, once again, you get a Q-polynomial subscheme. And I'll actually briefly mention this second result later. Also, Xiao-Suda has another generalization of this too, to intervals. where these designs are intervals, but I don't have it on my slides. But so a lot of these are these Q-polynomial subschemes coming up when you have tightness in these bounds for capital T designs. So by extension, I would extend Delsart's quotes conjecture a little bit more, and this is one of my motivating factors, that in general, Q-polynomial schemes should have interesting structure. And that's one of the things that intrigued me about this problem when Bill told me about it, is that examples of Q-polynomial schemes, apart from distance regular graphs, when we started working on this, were scarce. But the objects on the list were very interesting. So what else belongs on this list? And I found that very, very compelling problem. Okay, a few more facts about this before I get into primitivity and imprimitivity. So crime parameters don't have to be integral or even rational. How bad can they actually be? Well, fortunately, so we talk about the splitting fields. This is the field generated by the eigenvalues of the scheme. All of the parameters that you're interested in, these are all going to be contained in the splitting field. So we could ask, in the case of Q-polynomial schemes, how bad can the splitting field be? And Suzuki came up with a theorem. So if you look at the definition of Q-polynomial, you could ask, if I take the EIs, is there a way to reorder them so I also still have a Q-polynomial ordering of the idempotents? And sure, that's possible. Just like it's possible that a distance regular graph of diameter d, there's a distance graph that's also diameter d. That can happen. So natural question is, how many can you have? And he managed to prove that actually you can have at most 2 Q-polynomial orderings of a Q-polynomial scheme, and he was able to work out all of these. You should exclude the polygons, just the cycles. But now a corollary of this is immediately the splitting field actually has to be at most a degree 2 extension. And basically the idempotents have entries from the splitting field, and the Galois group is going to be acting on them. And so if you actually had a larger extension, you're going to have too many orderings for it to be possible. Okay, so either rational, but degree 2 is the worst that you can deal with. And I'll mention just one other result that's, I really just had no other place to put it, is just also it's known that dual to the Banai-Ito conjecture for distance regular graphs, that if you look at the rank of E1, which you can think of as the dual notion of a valency of a distance regular graph, and if you fix that rank, there are finitely many schemes with that rank that are Q-polynomial. Okay, so a few basic facts. The one at the top, though, is more important to the talk today. Okay, so I want to get into a little bit about what imprimitivity is like in Q-polynomial schemes. But to look at the definition, it's easier to start with distance regular graphs and just work by analogy. So in distance regular graphs, you're really talking about an association scheme, but it's generated by one graph in a nice way. And you can boil down all the parameters into just a collection of parameters that you can get everything else from. So we have these parameters B0 up to CD that basically are telling you if I have 2 vertices of distance I, how many neighbors of this vertex are distance I minus 1 from this, or how many are distance I plus 1 from this. So those are going to be the same given any pair of vertices at distance I. So these are just particular PIJKs, and every PIJK can be derived from it, and all the parameters you need, including crime parameters, all follow from this. Okay, so nice combinatorial definition. Now also, what do imprimitive distance regular graphs look like? Again, throw away the cycles. Then they come really in 3 flavors. So they're either bipartite graphs, they're either antipodal, which means distance d is an equivalence relation, or they could be both. Like, for example, the n cubes are both. For something that's just antipodal, like you could look at the the line graph of the Peterson graph is an antipodal distance regular graph. And these, we can put the conditions on these in terms of these BIs or the PIJKs. We can write all of these conditions in terms of those parameters. Okay, so now looking at Q-polynomial association schemes. How do we handle imprimitivity there? Okay, well, you can define these constants BI star and CI star, and they're just basically completely analogous with the PIJKs. You're just using Krein parameters. And similarly, you have these AI stars, though really everything's determined by these guys right here. Okay, now again, there's no known combinatorial meaning of those, but you can define, and this is Suzuki's theorem on imprimitive Q-polynomial schemes, you can define analogous ideas of Q bipartite, Q antipodal, or both, just using the same conditions with the Krein parameters. Now, I like this theorem for a couple of reasons, but one, it illustrates that just because something is straightforward for distance regular graphs, it doesn't mean it's straightforward here. It turns out that the dual to that theorem actually does hold, but it's a lot more difficult. And in the original proof of this, there were also two hypothetical cases that couldn't be ruled out, that had to be ruled out separately. The last one just a couple of years ago. So this theorem is now complete, that imprimitive Q-polynomial schemes have to be Q bipartite or Q antipodal. Okay, so or both. So once again, we have three flavors, but it's not a combinatorial definition. I don't have a nice statement for you right now as, like distance D is an equivalence relation or whatever. So what do these look like? So before I get into more examples, I'll now talk about work that's been done to say something about what Q antipodal and Q bipartite mean. What do these schemes look like? So first of all, a Q antipodal scheme has this property that we ended up calling dismantleability. Basically, it is an imprimitive scheme, and again, you can partition the vertex set into this system of imprimitivity. And certain relations appear inside the sets, and different relations appear between them. Now, the dismantleability property is actually that you can take any of these sets and throw them away, and you still have an association scheme, which is not in general something that holds in association schemes in general. Also, there's roughly half the relations are inside and half between. Furthermore, there was a bound on how many classes there could be, which I'll more or less skip over now. So there are some combinatorial properties there. And then later, Van Dam, Martin, and Musachuk said, well, if a black box tells you that the scheme is Q polynomial, and then you see this combinatorial information on top of that, then you know that it's Q antipodal. And so again, basically you have this kind of picture here where you can partition the vertices into a couple of different sets, roughly half the relations in or between. And what about Q bipartite schemes? Well, Q bipartite schemes, they look more like antipodal double covers. You have a relation that's perfect matching, and so the vertices come in antipodal pairs. And those are the ones actually I worked more on for two reasons. One, because Van Dam, Musachuk, and Martin were working very hard on Q antipodal, but also it seems that there are other Q bipartite schemes to be found. There's a construction technique also that works sometimes that I'll mention because it's a tool I use for finding new surprisingly for usually finding new primitive schemes as opposed to the other way around. So there's this is a dual to a theorem known in distance regular graphs on something called the extended bipartite double. So if you have a Q polynomial scheme and these parameters satisfy a certain relation here, then you can take this scheme and make a new association scheme from it, which is Q bipartite. And this is actually a certain kind of fusion of the bipartite double that I mentioned earlier. So I've taken it, I've fused some of the relations together in a certain way. I'm sort of glossing over one thing here. You know, how do you order these guys? There is a natural ordering of the AIs that you get by basically looking at how E1 is a linear combination of those AIs and looking at the different entries you get and ordering them according to size. Okay, so I actually tend to try to use this in reverse. So if you have some primitive scheme and it satisfies certain relations, you can construct a Q bipartite scheme from it. However, sometimes the Q bipartite scheme is the natural object. So sometimes you might find that first. So every time I run into a Q bipartite scheme, I ask myself, could it be the extended Q bipartite double of something else? And this amounts to cutting it in half in a nice way. And then you can maybe try to find new primitive schemes from that. Okay, and I'll briefly mention some other results. So this is a little bit out of place. Schemes both Q antipodal and Q bipartite. I mean, the things on the previous slides all obviously apply. But also there's some results here. This for 4 classes, these are just characterized as real mutually unbiased bases. This is a relatively recent result of Martin and 2 undergraduate students. And I'll also mention an infinite family of Q bipartite Q antipodal schemes that are not from distance regular graphs. This is one of the motivations behind the primitive in the Bane-Ito conjecture I mentioned earlier. There's this theorem. So I mentioned the bipartite double, that really very obvious construction technique. That if you do that to a Q polynomial scheme, usually you don't get a Q polynomial scheme. But if in the very rare case that all of these parameters except this one is 0, then you can, if you take the bipartite double of the scheme, you get another Q polynomial scheme. And it turns out there is an infinite family of distance regular graphs that have this property. And these are the Hermitian spaces dual polar space graphs. And so there's an infinite family. And this comes up sometimes. So this construction works, but very rarely. Okay, so now what I wanted to do was basically talk about examples of these schemes, because the problem I'm really interested in is finding more of these. And talk about the examples where there's been recent activity of some sort. So first of all, I've ignored in way too many talks the distance regular graphs that are Q polynomial. So I did want to mention them here. So first of all these graphs with so-called classical parameters. So there's a theorem of Leonard that says all Q polynomial distance regular graphs can be determined from 5, well, their parameters follow from 5 parameters. But Neumeier noticed that actually many of these graphs could be written in terms of 4 parameters, and they define the so-called classical distance regular graphs, which don't necessarily have big groups associated with them. It's a parameter. It's a condition on their parameters. And they're all Q polynomial, and many interesting objects are there. Hamming-Johnson, but also many graphs from finite geometry, like dual polar space graphs, are in this family. So I mean, it's not really doing it justice just putting a little blurb like that, but I could get lost in there very easily. Also graphs known as partition graphs, double covers of complete graphs, instance graphs of symmetric designs. Those give P and Q schemes. There's a list of regular near polygons in BCN that also are Q polynomial distance regular graphs. And then, of course, those, when D is small enough, everything wins. Okay, so now I'm going to depart from things that are P polynomial and just focus on those that are Q, what's known. So here are infinite families of Q, but not P, polynomial association schemes. So the ones with an asterisk next to them, this indicates there's been recent activity of some sort. So you have linked systems of symmetric designs. From Kasami codes, you can dualize because these are completely regular codes. And you get so-called relative hemisystems. I'll explain what some of these things are later. But d equals 3, we have these families. D equals 4, we have strongly regular decompositions of strongly regular graphs, so-called doubly subtended quadrangles. We can look at duals of extended Kasami code graphs, and again, real mutually unbiased bases in even dimension. Higman has some examples from triality, which give us d equals 5 Q-antipodal schemes. And then also there are infinite families with d odd. This one has an asterisk, though, because this is a recent discovery that I'll mention at the end. So here are the infinite families when it's q but dot p. And many of them have had some kind of recent results associated with them. And so what I wanted to do after I get through talking about a few sporadic examples is just sort of focus in on what's going on for these particular examples. And one thing that I find really striking when working on these problems is that I'm not disappointed when I look at Q-polynomial schemes. There's usually some reason why they're interesting that's independent of the Q-polynomial property. There's something else going on of independent interest. Okay, now on sporadic things, I won't dwell on them very long, but the Leach lattice gives birth to many things. Okay, and there's also, well, things like the Witt design or some quadratic residue code. There are some sporadic things that are associated to finite geometry. There is exceptional ovoids in certain quadrics that are giving a primitive Q-polynomial scheme, and I have not been able to generalize that. It doesn't seem to generalize, at least in the way I'm looking at it. A fusion scheme, I can't say I really understand here either, you know. And some sporadic things from Golay codes and different lattices. And also, well, I mentioned bipartite doubles. There are instances of strongly regular graphs. There, the condition, almost dual bipartite condition, is a lot less stringent. So you have these strongly regular graphs with strongly regular subconstituents, and you can take bipartite doubles of those, except for the pentagon, right? Okay, so I want to step away from the sporadic things and talk a little bit now about some of these infinite families of Q but not P. All right, so the first one I wanted to look at was linked systems of symmetric designs, which is, and as a forewarning, I guess the original definition allowed for the designs to have different parameters. I'm going to assume they all have the same parameters. But from what I understand, there aren't any examples known. Okay, yeah, that's interesting. So yeah, so that's an interesting open problem right there. So these were originally defined by Peter Cameron in 1972, and we gave an example that I'll mention on the next slide, but actually I can draw one up here. So basically, what's a linked system of symmetric designs? I take some 2 VK lambda symmetric design, and I take a bunch of sets of size V, as many as I can, but you'll see I can't do this indefinitely because I'm going to put some pretty strict conditions on this. What I want to have happen is, first of all, there to be between every 2 sets, I want an incidence graph of a symmetric design with these parameters. They don't have to be isomorphic, but they should have all the same parameters for what I'm going to do. But also, if I take 2 points, well, I point here and, you know, I don't know what to call it. It's a block from one point of view and a point from another. So what I want to do is look at their common neighbors down here. And if they're more blobs, I still just want to look at their common neighbors in one of these sets over here. And what I want is the intersection of those neighborhoods to take on 2 different values, depending only on whether or not these were incident over here or not. Now, another way to look at this, or something I find helpful to look at is, if I look at this as a design, and then I look at the neighborhood of a point over here, this is a particular kind of two intersection set in this design. And what I have is a nice system of two intersection sets in one design coming from another copy of a symmetric design of that order. Okay, so one example, because this is fairly easy to draw. So the 2-16-6-2 design, there are three of them. One construction of this is just to have your blocks basically be all the places a rook can move from a certain square, but excluding the square the rook is sitting on. Okay, so here are my blocks in the design, and I get 16 of them, one from each square here. Now, I'm going to draw circles to represent what are going to be blocks in a different design. So these are, say, two different designs coming in here. So these circles here represent blocks in now a different copy of this symmetric design. And this block can be seen to be a two intersection set for the other design. But now I can also push it around in the same way that I translate this block to get the others. And from that, I find that the blocks of one and the blocks of the other, they intersect in two different sizes, 1 or 3. And now what I can do is I can define incidence. So that gives me this design, that gives me this design. Now I want to define incidence between these two. Well, if the two blocks intersect in one point, I'm going to make them incident here and non-incident otherwise. And that'll give an example in this case of a linked system of designs where there are three of these. Now actually you look at this and it's not very symmetric, so you're like, oh, could I rotate that or something like that? And actually you can get up to 8 different sets here. All the same design, all linked together in this nice way. But you can imagine doing something that large is quite rare, and actually I'll mention that more on that on the next slide. So okay, so Van Dam in '99 showed that actually every Q-antipodal 3-class Q-polynomial association scheme is really linked system of symmetric designs. And so you wonder, well, what families are there known? And there's this family I mentioned, Peter Cameron's, where he has many of these, and this is coming from a group that has many, so I'm going to say this right, inequivalent doubly permutation representations, but with the same permutation character. Now, since then, Mathon searched, and for example, even on these two 16-6-2 designs, and found that you could link non-isomorphic ones up to a certain point. But the recent activity is that Davis, Martin, and that there should be a comma there. It's not Martin Pohill, it's Bill Martin. And, found some non-isomorphic examples, though I don't know how big can L get in that case. You have
I think we fall far short. I think we're half of what Peter got.
Roughly half. Okay, yeah, but non-isomorphic examples with the same parameters as this. So it's a general open question is which symmetric designs can you extend to linked systems? So there are many different families known, which are feasible and which can be linked. So here are some interesting open cases. I think I thought I'd just throw in a few small designs where it's known what the sigma and the tau would have to be. Can you even just, we have these symmetric designs. We know they exist. Can you just throw in one more class? Then you get something that's Q-polynomial, and it's not P-polynomial anymore. One thing that's kind of interesting when doing this is that when poking around with some of these designs, for some of them I couldn't even find one two-intersection set of the right size. And in the instant you can't find one of those, then you're just done. So So I wonder if in some of these families, maybe there's a very strong reason why they don't seem to complete. Maybe there just isn't even 1-2 intersection set of that type. Okay. So now to talk about some other families that I mentioned there was recent activity on. And a number of these take place inside generalized quadrangles. So I need to pause to define a generalized quadrangle. So it's a point line incident structure with a good deal of regularity. Each point is on the same number of lines. Each line has the same number of points. And of course, lines act like lines. You don't have two lines intersecting in 2 points. But then you have this last axiom for GQ, which is you take a line and you take a point not on it. There's a unique line through this point meeting this line. Okay, and in particular, there are no triangles in this incident structure. Okay, so I'll also briefly mention that you can dualize the idea of a generalized quadrangle. Just swap the words point and line everywhere. You have a dual quadrangle, and the S and the T up there just get swapped. Okay, and well, depending on the books you read, your definition might be slightly different. And let's see, this includes the grid. Maybe you don't want to include that, but more or less for what we're going to do, it's the same thing. There's some, the families which I'll need of generalized quadrangles are these, coming from finite geometry, coming from either symplectic or orthogonal spaces or this Hermitian surface. I get 4 different examples of GQ with parameters Q, Q squared, or QQ. And these come in dual pairs. This is, can be seen through the Klein correspondence and a little bit of work in this case, that these two are dual and these two are dual. And when Q is even, actually, these are isomorphic, but in general, they're not. Okay, so the first example I wanted to talk about was a relative, I mean, this is where I'm stretching recent the most because this was in 2005. So as deals with the notion of a hemisystem, you take a quadrangle of order QQ squared and you want to cut the points in half so that every line is cut in half by these sets of points. And Segre had constructed one in 1965 just when Q was 3, and it had been conjectured by Toss that none of these actually existed otherwise because there was no nice group giving one. And then in 2005, Pentilla and Casadente found actually that they exist in all prime powers Q. So, what does that have to do with Q-polynomial association schemes? Well, so it was known that hemisystems give strongly regular subgraphs. So in a GQ, if you take the points of the GQ and you connect them if they're collinear, you get a strongly regular graph. So what are we doing here? We're cutting that strongly regular graph in half. Well, you can look at the induced subgraph, and that turns out also to be strongly regular. And then Hammers and Higman define this notion of a strongly regular decomposition of a strongly regular graph. You just split a strongly regular graph into 2 smaller strongly regular graphs. And Van Dam, Martin, and Muzichuk showed that actually, in general, as long as you're splitting into 2 graphs with the same parameters, and well, there are exceptional cases when they're conference graphs, but forget about those, then you're getting Q-antipodal schemes. So you're getting Q-antipodal schemes this time with just 2 pieces, and relations between them given by, in a natural way, from the strongly regular graph that you've split into 2 pieces. Okay, so strongly regular graphs with strongly regular decompositions now come into play, and these hemisystems give an infinite family of examples. Now, for a hemisystem to exist, Q has to be odd. There's a parity condition. You can't do it if Q is even. But while looking for Q-polynomial schemes, so not actually trying to do something in geometry, looking for Q-polynomial schemes, we found out that there's an analog for Q even of this notion, and it gives us a family of Q-polynomial schemes. So I'll try to go through this quickly, maybe better in pictures than words. So take a generalized quadrangle of order q squared and take a subquadrangle of order q down here. And we say it's doubly subtended. So first of all, you can show that if you take all the points here and you take the points collinear with this point, they form what's called an ovoid. In this case, just think of it as an ovoid in the sense of PG3Q, and you're not far off the mark. In the GQ, all the lines down here are just meeting this in one point. And we call that doubly subtended. So this is the ovoid subtended by this point, and we call it doubly subtended if there are exactly 2 points that give you the same ovoid. And the classical example that I mentioned before contains, so we have Q4Q down here and Q5Q up here, and this is doubly subtended in there. So there is an infinite family of examples. And this was investigated by Matt Brown looking for semi-partial geometries. But actually, we found out this is really giving us an association scheme. So if we throw away this quadrangle up here and we look at different relations on the points here given by whether they're collinear or not and how these ovoids intersect down here, we're getting a Q-bipartite association scheme. And the antipodal pairs are just the doubly subtended pairs of points up here. And this is previously unknown. And it's not, in general, a Schurian scheme, though for q equals 4, it is. So then, again, I mentioned earlier, if I get a Q-bipartite scheme, I wonder, is it the extended bipartite double of something? So I wrote down what all the conditions of that would have to be and found out what I really want to do. So these are just the examples of those. But what I really want to do is cut the point set in half up here. So ignore this part. Cut these in half up here. And the lines that are up here, I want them to be cut in half. And there's going to be one point down here which is thrown away. And now there's no parity problem with the hemisystem. So we called those relative hemisystems. And from them, we were able to prove that actually if you take this classical quadrangle here and you find a relative hemisystem, when you split this graph, now we, instead of a strongly regular graph decomposition, we have 3 pieces. Then each of these 2 pieces up here, these are 3-class primitive Q-polynomial schemes. And this was an infinite family that wasn't known before. And again, was not a Schurian family in general. So this was the theorem of Quintilla and myself. This, of course, is only for Q even. Now, these are relatively pretty objects still. They're still vertex transitive. But Casadente went and proved a couple of theorems. First of all, he determined that if these are inequivalent, then also you get inequivalent association schemes. But also found uglier objects. So he was able to shrink the automorphism group, do some switching, and show there's actually a lot more relative hemisystems than the special ones that we found. And so there's a lot of examples with these parameters. Though it's still open in general, it might not be that bad of a problem if any scheme with these parameters must come from one of these relative hemisystems. Okay, all right, and now the last part. All right, almost done. So here are 2 natural questions. Which Schurian schemes are Q-polynomial, and which families have unbounded D? And when I was working on this problem, I didn't actually expect to really find infinite families answering either of these. But when I came back to this problem recently, again, looking at it with fresh eyes, the first thing I did was look for higher D. I'd focused a lot on D equal 3 or 4. And I started looking at 5 or above. And I found out actually there's a family sitting right there that just was previously not known. That's both of these, Schurian and Q-polynomial. So here's the basic gist. So it's a double cover of the symplectic dual polar space graph. So you take the symplectic dual polar space graph, And there's an operation known as the, this is one way to look at it, known as the Maslov index. Fix some determinants on these spaces. And we do this operation, and for maximals in the dual polar space graph, we get that the quadratic character of this is going to be plus or minus 1, and Q is going to be odd for all of this. So using this operation, we can attach signs to this scheme, this scheme on the symplectic dual polar space graph. And actually, this operation could be done on triples, and really there's a 2 graph here as well, tying into what Peter was talking about earlier. And admittedly, my co-author, who's Eric Morehouse on this project, is more interested in the 2 graphs than the schemes. So you do this Maslov index, and basically now you've attached signs to this distance regular graph. And, well, if you get a plus, now you take 2 copies of the vertex set. And if you get a plus, you go across. And if you get a minus, you cross like that. And you get a double cover. And so here are the basic relations defined in terms of the Maslov index. You know, we just take plus or minus, append plus or minus 1s to these spaces. And if this index is equal to their product, then that tells us whether it is or not, tells us which relation to give. And our new theorem is that this is actually a Q bipartite scheme. It has 2 Q polynomial orderings. And what's interesting, another thing that's interesting here is that for Q non-square, the splitting field is quadratic. Now, the other families that I've mentioned, well, distance regular graphs that are Q polynomial, if D is big enough, they have a rational splitting field. So we don't have unbounded D with an irrational splitting field. And the other example of an unbounded D, that bipartite double I mentioned, also has a rational splitting field. So this is the only example with unbounded D where the splitting field can be quadratic. So we need Q congruent to 1 mod 4 for all of this to work. Otherwise, it's not symmetric. And you need Q as a square for the splitting field to be rational. OK, so very close to closing. It's, you know, we're able to borrow some techniques from distance regular graphs in order to solve this. So it's not P polynomial, but for those of you familiar with this, it's close. It's very close to it. There's also a group description that we have in the symplectic group, which basically explains why it's Schurian, which I will skip. And one last thing is, are these the extended Q bipartite double of something? This is very interesting to me because I started computing parameters for what such a thing would have to look like. And the parameters look like a primitive scheme that's Q but not P, with D going to infinity. Now, there could be something wrong with it, but I've checked for like D up to 14, just on the computer, crunching out, checking to make sure that the Krein conditions work, and you know, the PIJKs are actually integers, you know, things like that. And so I can't find anything wrong with them so far. And they're Q but not P, but they're primitive. So as a challenge, because, well, there's a lot of other techniques, maybe there's some counting of subgraphs or something that can eliminate them. I don't know. And I'm very interested if anybody sees anything wrong with them. I also, though, it's not clear how to construct them either. But I just thought I would close. This is smallest open case for Q equals 9. These are parameters for a primitive Q but not P scheme, which would be the first part of this family. OK, and on that, I will close. Thank you very much.
Any questions for the speaker?
Oh, Bill.
So, what are some potential families with unbounded diameter related to this graph? So there are other things, other covers of this?
It's not looking good, yeah. So now so before I was looking mostly at low diameter, like D equals 3 or 4. Now I'm plowing through the known Q polynomial distance regular graphs, looking for that sort of thing, and I haven't had any luck yet.